Okay, thanks, Paul. Yeah, I'm Jaron Krogel. I'll be speaking today about statistical analysis and workflow automation with the NEXUS system. So, as a brief outline of my talk, in the first half, I'll be covering a statistical analysis of QMC time series data, which is essential for anyone who's going to practice Monte Carlo methods. Next, in the second half of the talk, I'll give an overview of the NEXUS QMC workflow automation system and what it is and how to use it. And then if time remains, I'll give a bit of an overview of the session 3 lab material, in which you'll be performing VMC, Jastrow optimization, and diffusion Monte Carlo with QMCPACK. Here are the basics that combine elements of both the workflow system and statistics, and I would encourage you all to work with those. Even if I don't get to cover them here, they are present in the GitHub repository. Okay, so for the first topic on statistical analysis, I'll start with something basic that I'm sure most are familiar with, but nevertheless is essential, so I'll include it. And that is background on Gaussian distributions and mean and variance. So Gaussian or normal distributions have this kind of functional form, this exponentiated form, which is the typical bell curve. The expected mean value, you just multiply the distribution by x to get the first moment of the distribution as the mean. And the variance is defined similarly as a difference between the second moment and the first moment squared. You get this sigma squared, which is the variance. Importantly, the variance is non-negative. It's greater than or equal to 0. And its square root, just sigma on its own, the standard deviation, gives you a measure of the width of the distribution. So over here, looking at the distribution, you can think of percentiles as measures of statistical significance. So if you have independent samples that are sampled from a normal distribution, then about 1/3 of them will fall outside, will fall away from 1 sigma of the true mean, and about 5% or 1 in 20 observations will fall outside of 2 sigma from the mean. Now, of course, we don't have access to an analytical distribution to integrate over like this. Instead, we take a number of Monte Carlo samples and use these simple summation formulas to estimate the mean and the variance with m statistical samples. And so these are approximate estimates of the mean and the variance. And because of that, those estimates themselves have a statistical uncertainty, which is important to account for. Now, in order to account for this, we can use the central limit theorem and introduce kind of what's ubiquitously called the error bar in our community. So the central limit theorem basically states that the distribution of mean value estimates is itself Gaussian distributed. In order to see that, let me introduce Gaussian random variables. So this eta, which is sampled from a normal distribution, a Gaussian distribution. You can think of eta as being the whole entire collection of samples that can be taken from the distribution. So in a sense, it represents the distribution itself. But why we're using them is because it allows us to do arithmetic, essentially, with probability distributions. So if you take the mean of this random variate, you get 0. If you take its variance, you get 1. Trivially, if you take a sum of independent Gaussian random variates, m of them, you get a new random variate, a new distribution. But now it's stretched, it's wider, and its width is increased by square root m. So that's the standard deviation, and the variance is now m. Okay, but how about the central limit theorem? So imagine now that you have a collection of different random variates, perhaps that are sampled from a distribution P. And this distribution can be fairly arbitrary, but we have to have essentially a bounded second moment. If the mean of every xi is x bar, and the variance of each of these xi's is denoted sigma x squared, then the sum of all these random variates, the sum of m of them, you're going to get a distribution which is shifted by m x bar. So shifted by m copies of the mean, and it will have a statistical uncertainty of square root m times sigma x. importantly, where this eta is now a normal distribution. Okay, so now let's apply this to the mean. So we take our estimate of the mean as before, represented by this summation formula, and we can just substitute in the sum formula directly in there, and dividing by m, you get this expression. So a statistical estimate of the mean is the exact mean plus this probability distribution with sigma x over square root m. So the mean, the estimated mean, follows a probability distribution. It has a statistical uncertainty that has a width related to the width of the original distribution and also the square root of the number of samples. And so to kind of illustrate that on the right here, this is the full probability distribution. If you take increasing numbers of samples, you get a distribution of the mean, which decreases in width like square root m. And this sigma x over the square root of m is the uncertainty in the distribution of the means, and we call that the error bar. So that error bar is going to be ubiquitous in the analysis of quantum Monte Carlo data. So it's very important to understand kind of where it comes from, what it is, how to make it smaller, and how to assess the quality of the statistical quality of your runs. Now, before we move on to more detail about the statistical analysis of time series, I'm going to dwell for a minute on the properties of the mean and the variance as they relate from a quantum Monte Carlo perspective through a few important quantities. So first, let me look at, we're going to introduce the variational and zero variance principles through this lens. They've been discussed before, but I want to look at them through the lens of these probability distributions. And the application is that you can use these principles to judge the quality of different candidate solutions or different trial wave functions. So let's start by kind of introducing a QMC energy distribution. You can think of this as an integral over a probability distribution of energies, but in practice, they're evaluated as an integral over electron positions, the 3n electron positions in real space, where you now have a probability distribution of those electron configurations in real space and some energy function. If you look at those, the VMC and DMC energies, they're given by this expectation value here for VMC. If you rearrange the terms, you can identify a probability distribution and an energy function, where the probability distribution is related to the square of the trial wave function, and the energy function is known as the local energy, which has this form. In DMC, it's of course similar. All you do extra is introduce this imaginary time projection function, which yields this fixed node wave function here. And the distribution now changes to this mixed distribution of the fixed node wave function multiplied by the trial, and the local energy remains the same. Okay, so what are these two principles and what do we get from them? So the variational principle first. So you have the Schrodinger equation, and imagining that psi here is the exact ground state, you just have this simple eigenvalue equation where E is the ground state energy. And this statement of the variational principle is that that the estimate of the energy in QMC is always greater than or equal to the true energy. But more important, well, just as important, perhaps more importantly, that as the trial wave function approaches the exact wave function, the QMC energy approaches the exact energy. And so in this case, lower energies correspond to better trial wave functions, and they get you closer to the true energy. Okay, now the zero variance principle. So trivially, the variance of any energy distribution is non-negative. It's greater than or equal to zero. But importantly, in quantum Monte Carlo, the variance itself goes to zero as the trial energy, a trial wave function approaches the exact one. And so similar to the variational principle, here lower variances correspond to better wave functions. And so you can evaluate them independently. I'll kind of illustrate this over here on the right. So if you have the exact wave function as your trial, you're going to get an energy distribution of zero width. centered right at that exact energy. If you use a trial wave function, for example, from Hartree-Fock, it will be centered in VMC at the Hartree-Fock energy, and it will have this fairly wide width. If you use a better wave function, like a Slater-Jastrow form, the energy will reduce, and you'll also have a narrower width to the energy distribution. So an important point here is that better trial wave functions simultaneously result in better or lower energies, and also smaller error bars, smaller statistical uncertainties. And that means you can gain a fixed statistical uncertainty with fewer samples. And so that's an efficiency gain, and that efficiency gain gets better and better the closer you get to the exact trial wave function. Okay, the next QMC topic that I want to go over is the scaling of the QMC energy and the energy variance. So we know already that the total energy is extensive, or in other words, it scales linearly with system size as you add more atoms, or it's size consistent. But what is the system size scaling of the energy variance? So in order to get at that, imagine that you have a collection of atoms, well-separated atoms, and each of them has some energy distribution, p atom of E. So from these single atom energy distributions, you can get energy samples. The mean of each is this mean energy for the atom. And the sigma squared, the variance for the energy distribution of a single atom is this sigma squared E atom. Okay, so now let's apply the central limit theorem. The total energy is just the sum of the energies of the atoms, like this. And from the central limit theorem, we know that becomes n times the energy of the atom. That's just the size extensivity. But then you get the statistical uncertainty, which goes like square root n sigma atom. So directly you can read off from this that the total energy is ne atom, size extensive, and the variance also scales linearly like n. It is also an extensive quantity. So from this, we can introduce the variance to energy ratio, which is an intensive quantity. It doesn't depend on the system size. And we found from experience that it's a transferable metric across different systems, whether you make a molecule larger, or even if you include heavier elements with a larger Z, for example. And you can use this as a more or less global measure to judge wave function quality, which is useful, for example, when you're performing wave function optimization. Do you know whether or not you've optimized well enough, far enough? And so any decent wave function will have a variance to energy ratio of more or less than or equal to 0.04 Hartree. Now that's not a great wave function. Anything with a variance to energy ratio larger than this, you should essentially throw out and try and do better. In practice, your target should be more like 0.02 or 0.01. And that would represent a good quality wave function. Okay, so those are some of the QMC topics that relate to energy and variance. Let's go back now to time series themselves. So an important topic here is accounting for temporal autocorrelation. So what is autocorrelation? What it means is that adjacent Monte Carlo data samples are not independent from each other. And as a result, the statistical error bar, if you compute it naively, is underestimated, because in the end, if you account for autocorrelation, you'll have fewer effective independent samples. So what do time series look like that are uncorrelated and autocorrelated? So this is an example of uncorrelated samples. What you can see essentially is that the next sample in the series can vary widely. It goes over the whole distribution, doesn't matter where it was before. Autocorrelated samples, by contrast, you can see that there's a spatial variation that persists over many samples. In other words, one sample is somewhat tied to the previous one. It can only depart so far from the previous one. And this is accounted for as an autocorrelation time. So the error bar nominally now is is the variance over the square root of an effective number of samples, where that's the original number of samples divided by an autocorrelation time. This is information about the autocorrelation time is encapsulated in the autocorrelation function, where you can look at the linear correlation between different Monte Carlo samples differing by some interval in time. And that autocorrelation function, for example, can look like this, or have like an exponential decay. From this, you can estimate the autocorrelation time for this time series would be about here, or about a length of 8 samples. And that will increase your error bar appropriately to account for the true statistical fluctuation of the mean. And this must be accounted for in all Monte Carlo data. And it's particularly important in diffusion Monte Carlo. So where does temporal autocorrelation come from in Monte Carlo? Or really in quantum Monte Carlo. So where it comes from is that in both VMC and DMC, you create new electron positions from a drift diffusion Green's function. So in other words, the distribution of the new positions is created from the distribution of old positions through this kind of this Gaussian transition matrix. And this chain of configurations in space is known as a random walk, where the new position comes from the old position with a linear drift term, linear and imaginary time, plus a diffusion term, a Gaussian distribution with Witt's square root of tau, the imaginary time. And so these samples can only get so far away from each other spatially. With a large time step, each step can get fairly far away from the previous ones, and you might have a short autocorrelation time as a result, because the points now arrive at places in the energy distribution that aren't very related to each other. Whereas if you have a very small time step, then you can see here, this is an example of a random walk with a very small time step, and you can see that the samples remain very, very close to each other. So neighboring samples will appear at close by positions in the energy distribution, and they're no longer independent. So autocorrelation also relates importantly to a concept known as statistical equilibration, sometimes known as burn-in in Monte Carlo sampling. And what this means is that it takes a while for the Monte Carlo step for the walkers to begin sampling the equilibrium distribution, the one you really want. So the random walks, why is this? Well, the random walks often start with arbitrary or low probability samples, positions in coordinate space, sometimes known as out of distribution samples. Here I show a variational Monte Carlo time series where the equilibration time is rather short. It's been estimated here. It doesn't have to be this short. Sometimes VMC can start further away, but it's careful to monitor this. Diffusion Monte Carlo, by contrast, starts from variational Monte Carlo samples. When you start DMC, the distribution evolves because the VMC and DMC distributions differ. In general, it decays more or less exponentially in imaginary time as you do more and more samples, and eventually it reaches its equilibrium distribution and is equilibrated way out here. Now, it's very important to know where this equilibration point is, because if you include all of this data to compute your mean, you'll be severely biased. And so all the samples in an equilibration period need to be thrown away prior to any statistical analysis. So here, this is showing diffusion Monte Carlo with a relatively small time step, and you can see that we only have about half of the data from the DMC to perform statistical analysis. That's pretty inefficient. So how can you improve that? Well, you know that you can decorrelate or create samples that are further apart in configuration space by using a larger time step. So you can run VMC as normal, run with a larger time step to get down this exponential curve and arrive at a distribution that's closer to the small time step distribution. and then switch to the smaller time step you want, and it results in a very short equilibration time, and you get more useful DMC data. So it's just one thing I'd like to make everybody aware of. In addition to accounting for it, there are ways to reduce it. All right. As a final statistical topic that's fairly basic but crucially important is being able to estimate the uncertainty in energy differences. So the applications here are to correctly assign the statistical error bar of energy differences and to assess whether two values differ with statistical significance. So imagine now that you have two energy estimates, which are Gaussian distributed as before. So one with a mean of E1 over here and a width sigma 1e. So this is its error bar, and this is the distribution, and a second estimate of some other, maybe some other system or some other trial wave function. We have a different energy distribution here with a different mean and a different width. And what you want to know is what is the difference between these energies. Well, if you do that, if you just take the difference between these energy distributions, you get the difference in the mean energies, that's what you want, plus a broadening. And it's important to see that this distribution is wider than either of these two on its own. Taking an energy difference broadens the distribution, and the error bar of the energy difference, its statistical uncertainty is just the square root of the sum of squares of those individual distributions. And now to assess statistical significance, how do you know if the energies differ? Well, you can decide based on this inequality, where n is the number of sigma in which they may differ. So to get n, you can just divide this energy difference by the statistical uncertainty. So do the energies differ? Well, if n is less than 1, basically you don't know. There's little evidence that they differ, and you might reasonably conclude that they're the same within the statistical uncertainty you have. What if n is about 1? So maybe they differ, but there's still a 1 in 3 chance that they're the same. What if n is 2? Well, they probably differ, but again, there's still a 1 in 20 chance that they're the same. So if you're making a bunch of different energy difference estimates, you're bound to get ones that fall within, that they could be the same, or they could be different, but you're estimating them to be the same. But if you take n to be 3 or higher, it becomes highly likely that they're different. There'll be less than a 1 in 100 chance that they are the same. And why would you want to know this? Maybe you want to understand whether two different steps in the optimization are the same or different. Has your optimization converged? Or, for example, in a binding energy, you want to know what the binding energy is between two separated atoms and a bound molecule. This gives you a way to estimate the uncertainty in that and how well you know what that is. Okay, so those are the statistical topics. I was going to stop for questions here, but in the interest of time, I think I'll leave them all to the end. And next, I'll be talking about the NEXUS workflow automation system, which is designed for quantum Monte Carlo workflows, one of which I show here. A scientific workflow is essentially a cascade of different simulations you might perform to produce an outcome. And you would do that with different simulation codes. This might take a fair amount of work by hand. In other words, it take you a lot of time. And if you do it by hand, we'll introduce potentially a bunch of errors. Okay, so as an overview here, the goals of a workflow system here are to make QMC calculations more accessible. In other words, we want to have a less steep learning curve for new users. We want to automate away the time-consuming steps in the simulation process. In other words, just to speed up your research. We want it to be hands-off. In other words, you don't need to compose or edit large simulation input files by hand, but you want to be able to have that be done automatedly with a small amount of information. You want to be able to enable large-scale job submissions on a variety of supercomputing platforms without your input specification for the workflow system needing to change much as you go across them. You also want to have these simulation workflows to be scriptable. In other words, make it easy to scan over, say, different DFT functionals for the trial wave function or a whole bunch of molecules in a high throughput fashion. And finally, we'd like to support every type of calculation possible with QMCPACK so that you can do what you want and provide documented examples. Now, this is still aspirational, but support is broad. Okay, so what are the core features of NEXUS? Well, NEXUS, the workflow composition for NEXUS is done in Python, and a Python script essentially comprises a meta input file for the execution of all the simulation codes involved in the workflow. It brings all the different simulation programs, whatever they are, whether they're DFT or QMC, together in a single coherent framework, makes them easier to work with together. It automatically generates input files from a minimal amount of user input, so it simplifies things. NEXUS also enables job monitoring, so it automatically executes simulation workflows and monitors them all until they're finished. It also makes analysis easier because it can extract simulation results and make them accessible within the user script itself. Okay, so what codes are supported by NEXUS? Well, of course, it supports QMCPACK. It also supports like quantum chemistry codes with Gaussian basis sets like GAMES, PySCF, and quantum package. In the land of solid state, it supports the DFT, plane wave DFT codes, VASP and quantum espresso, and also mostly for periodic systems, the real space multigrid code. All of these, with the exception of VASP, directly interface with QMCPACK. Okay, so what about the workflow execution and monitoring with NEXUS? So what are workflows exactly? Well, here's a very simple molecular solid state workflow that you might do in QMC. For example, maybe you're calculating the total energy of coronene or diamond. You'll start with a DFT calculation with PySCF or quantum espresso. Next, you'll convert, say, the orbitals that comprise the Slater determinant with convert for QMC or PWQMCPACK to convert from the native format into one that QMCPACK can read. You might perform JASTRO optimization with QMCPACK and then feed that JASTRO into DMC for a final run there. So each of these boxes is just a simulation run. Each of the arrows represents information that's passed between the different simulations and form dependencies for the sequential execution of these. This is a very simple linear workflow, but NEXUS can support more general branching workflows that are known more formally as DAGs, directed acyclic graphs. And it can manage as many of these as you want simultaneously. So any number of workflows all at the same time. It can tell whether they can all be, which of them can be executed simultaneously, and if so, it will run them simultaneously, and also form a batch queue basically internally for all your simulation runs. So for example, if you have a beefy workstation, it could keep the workstation busy around the clock without you having to watch it. Or equivalently, it can submit a bunch of jobs to a batch queue on a supercomputer, process the dependencies, and introduce new simulations into the queue as they become available. Okay, so what does working with NEXUS look like? So from the point of view of installation, first you just download the necessary code. In this case, you just download, you git clone QMCPACK, because NEXUS is packaged with QMCPACK. And then just go into the NEXUS directory. After that, the install is quite simple. You just export two paths in your shell environment. One, you modify the Python path to point at the NEXUS library, and the other, you put the binaries, the NEXUS binaries in your path. At that point, that's it for installation. NEXUS needs a minimum in addition to the Python standard library of NumPy. So if you have NumPy, most everything will work. There are additional optional packages for specific features that are less used, which NEXUS itself lists, or they're also included in the user manual. Once you've installed NEXUS, it's a good idea to test it. That's done with this NEXUS test binary. So if you run it, it will give you a whole slew of different tests, actually many more than 16. It should run in less than a minute. And if all the tests pass, then you can assume it's safe to use NEXUS on that particular machine. If you get failures, please report those on GitHub to the developers or via Slack or email. Because that might point to some important bug with NEXUS in a particular environment that we'd like to know about and to fix. Okay, so again, working with NEXUS from the point of view of user script composition. So what does it look like to tell NEXUS what you want it to do? Well, this is an example Python script for a simulation run similar to that DAG shown above, that linear workflow, a little simpler because we're not doing wave function optimization. So you start by invoking the Python interpreter. You import a set of functions from NEXUS, which we'll go over in a moment here. And then you sequentially tell it what you want it to do. So the first thing is you supply some general settings. For example, you tell it where your collection of pseudopotentials are. You tell it what kind of a machine you're running on. In this case, it's a 4-core workstation, as in the lab. You can change this number 4 to any number that you have if you have that many cores available. For supercomputing machines, this also changes, which I'll go over later. Sleep is a polling frequency in seconds. So in between, so NEXUS monitors the workflows with successive polls. So in this case, every 3 seconds, NEXUS will wake up, look to see if anything's completed that it needs to process, and see if there are any jobs ready to submit. After that, it will go back into a sleeping state in between. Now, while it's in a sleeping state, of which it will comprise most of its time, it consumes almost no resources. So in this way, NEXUS is appropriate to execute on head nodes of a supercomputer because essentially it won't have any noticeable impact on the computation being performed on that node. It won't slow anything else down, except for the necessary information that's needed to create new input files, pass information around, that sort of thing, which you would need to do anyway. These two flags, the status and generation flags, I'll cover a little more later. Well, let me just mention this generate flag. This will run the workflow in a kind of a dry run mode. You can check this way to see if your workflows themselves are correctly composed before you run for real. And we'll look at the status one in a moment. Okay, so what about the actual action in the workflow? Well, first you have to specify what physical system you're running on. So here, for example, is a periodic example for Diamond. You point it at a structure. In this case, you can provide it a POSCAR file, an XSF file, an XYZ file, whatever. It will pull out all the atomic species and their coordinates from it. In a periodic system, you might want to tile it. So in this case, take a 2-atom primitive cell of Diamond and tile it by 2 in each direction to get a 16-atom unit cell. Then again, for periodic systems, you can specify a Monkhorst pack mesh of the twists. For the supercell, in this case, it's just doing a single twist at gamma. And then finally, for both periodic and molecular calculations, you specify the Z effective for each pseudopotential species you're using. So in this case, with carbon, we're going to be using a neon core potential. So instead of a valence of 6, it has a valence of 4. Okay, after that, we specify the different simulations you want to perform. In this case, we're going to start with a PWSCF calculation. The inputs for PWSCF are just listed here. You'll notice if you're familiar with PWSCF, these keywords here are exactly as they appear in the input. And then there are some other standard things that NEXUS reads, for example, the physical system, what pseudopotentials you're using, path where you want the simulation to be performed, an identifier or prefix to the input files and so forth. And then an important one is information about the job that you want it to execute. In this case, on a workstation, you tell it that this particular run for PWSCF can occupy all 4 cores. In this case, the number of cores can be anything less than 4. Next is the orbital conversion step with QMCPACK. It doesn't require very many inputs here, just a few of the standard ones, plus, importantly, a dependency. So this is telling it needs that before this conversion can run, SCF needs to finish, and it's going to collect the orbitals, or in other words, the path to the orbital file, and to make it available to subsequent calculations. Okay, finally, you generate QMCPACK. Again, simple standard inputs. Here, much like before, in this case, running with no Jastrow factor, and importantly, providing calculation details. So here we're just going to do a single VMC calculation. This will, with just one walker per core, the number of blocks and steps, and the time step, and it will generate everything from there. Finally, this run project function, this is where the actual action happens. This is where the workflow is executed. Up through all of these steps, nothing happens. But right here, once it reaches this point in the script, it will begin executing the simulations on your machine. Okay, so what does it look like from a user point of view to execute NEXUS? So if you want to, you can look explicitly at the DAG of the simulation workflows here with this -- graph sims keyword that you feed to any NEXUS script which you've provided. In order to see this, you'll need the PyDot library installed. A standard thing to do is to look at the status of your simulations. That's with the status only flag. And in this case, it will show you each of the runs, where they're going to be performed, what their identifiers are. So an SCF run, a conversion run, the VMC run. These are status flags. In this case, nothing has happened yet. This flag is whether the run has completed successfully or failed. Of course, nothing's happened, so nothing going on there. When you actually execute the workflow, so just running the script without any other input flags, NEXUS will start up. It looks like this. There's the first poll. It will create and enter the SCF directory and execute these 2 commands, which it will show you. So it's just doing a simple MPI run to start up a Quantum Espresso. Here are successive polls while it's waiting for that run to finish. Here it does. And then it creates the next directory for the conversion step, executes it, waits a little longer, and does the same for the VMC. Until, as it waits, the VMC is finally finished. Once everything's done, you'll see this project finished written to the output. And after that, after everything's done, you can look at the status here. Again, looks similar to before, except now all these flags are 1. That means it's done everything for each of the simulations, and none of them have failed. These numbers here are just the process IDs on your workstation, or they're the number that, for example, the batch submission system connects with your run on a supercomputer. Finally, here you can process the outputs. Pretty simple. For PWSF, for example, you're just grepping out the total energy. For QMCPACK, you're going to use the QMCA tool, which has been shown a little bit about before, but with time we'll might discuss a little more about, and certainly you'll get to have much more detailed experience with this in the labs. Okay, so what's it look like to work with NEXUS from yet a different point of view if you're going to run on different machines? So we've already covered here what it looks like on a workstation. the two things that change are what machine you're running on and what the jobs look like. In this case, on the workstation, all you care about is how many cores you're running on and what type of threading you're using. So 4 cores, 2 threads, create 2 processes, each with 2 threads each. That's 4 cores running QMCPACK on the workstation. If you switch to an institutional cluster like CADES at ORNL, the name of the machine changes. You're running on CADES. You might have a user account for the queue you're running in to charge hours to you. And then the job, instead of specifying cores and threads, you're likely to be requesting a certain number of nodes, a certain number of threads, and also a wall time limit, right? 8 hours here. And because NEXUS already knows about CADES, it knows how to create the Slurm, the SBatch submission file here, which it will automatically generate and produce the execution line and submit this batch job for you. So you can see you didn't have to specify much information here, and it created all this for you. You don't need to worry much about it. As you go up to a much larger system, things look very similar. I show an example here for Perlmutter and NERSC, which some of you may have access to. So it looks very much like the cluster. Perhaps you're going to be asking for a larger number of nodes. But again, it generates this submission file. It looks different from the one over there at this other machine, appropriate to the machine you're running on. So I hope you can appreciate that the rest of the user script doesn't change. You only had to make these small localized changes, and you can scale up from a small workstation all the way up to a leadership computing resource. And this is useful because different steps in the workflow require different levels of resources. For example, you might be able to run the DFT affordably on a workstation or a cluster, whereas QMC, for medium runs, you might need a cluster, or for large ones, you'll need a large-scale computer, a large-scale supercomputer. And NEXUS can account for that and let you switch between these environments and continue those workflows at the scale that you need. So what computing environments are supported by NEXUS? What's it already know about? So it already knows about machines at several large facilities in the US. At NERSC, it automatically supports Perlmutter. At the Oak Ridge Computing Facility, it's the Frontier and Andes machines. At the Argonne Computing Facility, it's Aurora and Improv. At Sandia National Labs, it knows about Skybridge, Serrano, several others. And at NREL, it knows about Kestrel, in addition to many other institutional clusters elsewhere. Adding a new machine is pretty easy. So if you want to add a new one to support your local cluster or supercomputer at a particular university, it only takes about 30 lines of Python code. Here I show what it took to add Kestrel to the system, just making a class deriving from one of the NEXUS standard classes. And most of what you're doing is just telling it how to write that batch submission file with all the standard flags that you want, and how it pulls different information from that job object to populate that submission script. Once you've done this, NEXUS can submit jobs for you on that machine. If you do support new machines that other users could make use of, then I would encourage you to make a pull request to the QMCPACK repository so that your changes can get merged in and others can benefit from this work that you did and run NEXUS on their machines easily. Okay, finally, where do you learn a little more about NEXUS? So NEXUS and QMCPACK documentation, you've probably seen where QMCPACK's documentation is on this Read the Docs. The NEXUS manual also resides on a Read the Docs page. Here, this user guide is a little bit minimal. It covers more of what NEXUS is, what it can do, and some more details about what I discussed. Probably the best way to learn more about NEXUS is to look at user examples, of which there are many included in the QMCPACK repository, and some of which you'll have the opportunity to work with in the labs. Okay, so in summary, proper statistical analysis is essential for QMC practitioners. So knowing about statistical significance, accounting for autocorrelation and equilibration, correctly applying the central limit theorem. It's all stuff you're going to need all the time as you run QMC. As we noted, QMC calculations are actually workflows of interconnected simulations or calculations, and we've shown how these can be managed efficiently with the NEXUS workflow tool. Looks like I have a little bit of time. I'll just take a couple minutes here to give you an idea of what the lab examples are.
Take all the time you need, Jaron.
So I'll give a little bit of an overview of these different labs on the virtual machine that you'll get to do. So to access the lab material, just navigate to the summer school main link on GitHub. They're in session 3, statistics and workflows. So you should come to a page that looks like this online. And down here, you'll see as you open this in your browser, you'll see a README. That's kind of the top level README that introduces you to all of the labs. And if you navigate into each particular directory, what you'll see is specific READMEs that guide you through each particular sublab there. So in order to work with the labs, you need to fire up the virtual machine, which Paul covered in his prior talks. So if you need a reminder, please go visit those. In order to run them, just go in the summer school GitHub repository, perform a git pull. If you haven't done this for a little bit, this will update all the information in the GitHub repository to include all of these labs. And then just go in the lab directory and follow the READMEs to execute the NEXUS workflows and do the analysis from the command line. Before going into the specific labs, I'd just like to give some indication of this QMCA tool, which you'll be using to perform statistical analysis of data that comes from QMCPACK. So for example, you can produce a trace plot. In other words, the statistical time series here using QMCA. In this case, you pointed at a scalar.dat file that contains information from QMCPACK about the run. Here you're saying you want to show the quantity, which is the energy. You're just going to assume for a moment that the equilibration time is 0. And this -t is what makes the trace, specifies the trace plot. In order to remove the equilibration period, you can view this trace plot and decide where the run is equilibrated. Say, for example, at 100 steps or 100 blocks, include that here. QMCA will output the local energy plus its estimated error bar, including autocorrelation. If you want to check what the autocorrelation is, you can have QMC show you the autocorrelation it estimated. That'll be shown as a number over here. So in this case, it estimated it as 5 blocks. And you'll want to have the number of independent samples be something more like 100. So if you had 800 blocks here and you divide by 5, you want to check that that number is large enough so that your error bar is computed well enough, that you have enough samples to know what your error bar is. Okay, what about some of those other quantities we talked about? Not just the energy, but the variance and the variance to energy ratio. So you can ask for that by saying -q quantities of energy and variance. And if you do so, it'll give you the local energy as before, also the variance in Hartree squared, and that variance to energy ratio for all the scalar.dats you pointed at, say with pattern matching. In this case, you're doing an optimization run with several iterations or perhaps epochs in the machine learning parlance. You can see where it started, the wave function was very poor. But after even just one step of the optimization, you're at a variance to energy ratio of 0.02. And so you've already arrived at a pretty good wave function just in that first step. To learn more about NEXUS and get a more complete picture, there's more complete documentation at this link. Finally, just a brief overview of the examples. In the first one, we'll be looking at the equation of state of diamond, just with quantum espresso. Here, the goal is just to compute the diamond energy versus volume at 7 lattice constants, just to gain a basic familiarity with NEXUS and learn the major functions in the user script. We'll get into QMC examples. The rest of them will be using the lithium hydride molecule. In this case, just doing a simple Hartree-Fock followed by VMC. The statistics topics you'll get to learn more about are estimating the equilibration time, estimating the mean, the variance, the error bar, estimating the autocorrelation time, and how to predict and obtain more precise estimates. In the third example, we'll now introduce Jastrow optimization. So you'll learn more about the two-body Jastrow form and performing Jastrow optimization with the linear method. We'll go over more about judging the quality of the wave function optimization and assessing the energy differences in convergence to know whether you're done with the optimization. Okay. Fourthly, now add diffusion Monte Carlo. Topics here are to see more about this exponential equilibration in DMC, study the longer autocorrelation time in diffusion Monte Carlo due to the necessarily smaller time step, and performing these topics which I haven't covered much about, DMC time step extrapolation to get the high quality estimate, and look at population control bias, as well as resampling fits to statistical data. Okay, that's what I have, and I'll take questions.
Thank you very much, Jaron. So thanks for the presentation on the slightly tricky topic of statistics and then going through the NEXUS workflows. We do have a couple of questions on Slack. The ones on the chat have been, on the Zoom chat have been answered. So first of all, here's a question about NEXUS from Reza. When I started using the NEXUS workflow, the first thing that was a challenge was to find out which arguments can be used for a particular workflow composition. So is there a way to see which inputs are available? So for example, in an optimization workflow, what minimization methods are supported, or if using a two-body Jastrow, what inputs are required. So what's the easiest way to find out what is supported? I'm obviously thinking there's lots of examples that might be a way to get a starting point.
Yeah, so for QMC runs, the easiest way to learn what's supported is by looking at the examples under the NEXUS examples directory. There are many more than I showed here. There aren't actually very many inputs that are supported or needed and hence supported for QMC calculations. If you know maybe a dozen, then that's essentially everything you'll need. And so those are all present in those examples. You'll see them from a couple of different perspectives because that's for quantum Monte Carlo. For codes like PWSCF and games, if you look at the user manuals for those respective codes, they have huge lists of keywords. You can enter any of those keywords into those generate functions for PWSCF and games, respectively. It knows all of them. So more or less, instead of providing documentation, I'll just defer that to the respective documentation from those codes. For PySCF, PySCF itself works with a Python code, Python generated input. So there it assumes that you have some familiarity with PySCF already, that you know how to make a user script. But there are anchor points where NEXUS will insert, for example, information about the physical system at the beginning and information about wave function conversion at the end. But following the examples that are there for PySCF, you'll see exactly what those are. It's fairly basic. But with that, you can create basically a more complicated PySCF run, but that's up to you in creating the template for it, because NEXUS couldn't possibly generate all possible Python scripts for PySCF.
Thanks. Yeah, I think that answers it. And next, a question from Array that I will take a crack at answering and then let you add some extra comments if you have any, Jaron. So Array asks, How does one check for the population control bias in diffusion Monte Carlo? So how do we know enough walkers are used? Do we assume it's smaller than the fixed node error? Running the same job multiple times can be quite expensive. So is anything built into the workflow? And Ray, that's a great question. And I think actually that leads into what will be our next session, which on Thursday will be going into examples of running molecular calculations and presenting more background on that. Obviously, there's a dependency between presenting the workflow tool to run QMC calculations and having explained the QMC calculations, which then need the workflow tool. So I think we may have an example in Thursday's presentation. But what I want to underscore to answer your question is essentially all the choices that we're making in Diffusion Monte Carlo are indeed testable. So one can go out and test them. So what one should do when setting up a system for the first time, or where there's no published literature where people have already investigated this, is actually to check for this. So one might start with, say, 1,000 walkers, do the statistical analysis that Jaron explained in the first part of the talk, and then say increase to 4,000 walkers, and then you can see has the energy or indeed any other property you're interested in varied in a statistically significant manner. So one can test this, and because the workflow allows you to run a DAG, you could potentially set that up all in the same initial NEXUS script, and it would go off and run both calculations for you. So ultimately, one has to test or have a trusted paper in the literature to point to where you can get numbers from. Of course, once you've done this for one sort of composition of a system using the same Schütte potentials and combinations of elements, you'll have the more or less same population control biases, and indeed any other sources of error will be very similar. So it's not normally necessary to test for every single calculation that you're doing. One normally just checks once, much as one picks a time step for the given system. But Jaron, would you like to add any more to what I said?
Yeah, let me add a little bit more about population control bias. So population control bias arises from a combination of two factors. One is fluctuations in the local energy, and then the feedback scheme that's used to control the population itself. So the population control bias then, because of those two factors, scales like the ratio of the variance divided by the population size. So it's inversely proportional to the population size. The larger your population, the smaller it gets. But also the larger or more complex your system gets, in other words, has a larger variance, population control bias will creep back in. As Paul says, the best way is to explicitly check to do independent simulation runs. For most systems of typical use cases, I'd say medium scale systems, you'll find as a good rule of thumb to use at least 1 or 2,000 walkers is generally sufficient. You should analyze that for at least one representative system to see. At that level, it's often smaller than the fixed node error. As you go to really large systems, though, you might want to kind of recheck it again. And a healthy habit would be to occasionally, not every time, but just occasionally run with, perform your typical run and then run with more walkers and see if anything changes at all. But one benefit of going to larger system sizes, you need more computational resources. Typically, those are done on much larger machines. And as a result, you kind of naturally get a much larger population of walkers. So it hasn't often crept up to be an issue.
Thanks, Jaron. And we have one more question, after which I think we'll wrap up for the day as we're running a few minutes over. So this is a question from Chung Yu about Nexus workflows. It's two related questions. One, does the DMC run automatically from the result of the last VMC step and no further care is needed? So a question on how the dependencies are done. And then what is the layout of the output?
Okay, so within QMCPACK, it executes a simple DAG itself, a linear one. So in QMCPACK, in the input, you specify successive QMC runs. And so to run Diffusion Monte Carlo, one doesn't typically create a separate VMC run, but typically one puts in the input file explicitly a short VMC run followed by DMC. And that's done automatically within QMCPACK. Now with each QMC input block you add, it creates a different set of outputs. Same structure, but different indexing. So it's known as the series in QMCPACK. So the first one you put will be series 0, the second one series 1, the third one series 3. And so you'll see in the output files, like in the scalar.dats, etc., you'll have like an S000 in the file name. That's series 0. That might be, in the case of DMC, that's often variational Monte Carlo, where series 1 or series 2 are probably correspond to the DMC sections you put there. Does that sufficiently answer
Yes, thanks very much, Jared. I think we should wrap up here. So thanks very much, everyone. Thanks to the presenters and thanks for the good questions. You can keep asking questions on Slack, of course, and hope to see everyone online on Thursday for our molecular tutorials. Thanks, everyone.